Okay, so let's some technical issues. Um, so let's see. I suggest we take a brief summary of what we covered last class, especially the last part. Okay, we talked about choke. We discussed a bit the liquid choke, which is, you see there? Okay, we this looks strange, right? Can you see okay from there? Yeah, more or less. Okay. So we went to the liquid equation, right? Like I told you, there are not many chokes that work in just liquid, okay? Because you usually have either multiphase flow or you have gas. But it's interesting our discussion to discuss, the effect of the opening or the position of the stem in an adjustable choke. Then we went to the gas development, which was more complicated, but we were a bit used to it from the gas IPR, right? That we have to stick the expression of density. We had to assume an adiabatic process, and then after that, we were able to find this last equation, the last equation of the gas. Okay, using the same principle between the inlet and the throat. And then we stick in a factor that we will change to adjust, we know that the fluid in the throat doesn't go through the whole area, but it goes through the vena contracta, and that coefficient is just to adjust for that. Then we did an exercise. We said, well, from this previous exercise, we know the delta P that we need of the choke. And then we went to the Excel sheet and calculate. And we saw, well, actually, that gives you a higher rate. Okay, the rate that I want it was 1.25 or 35, I think. Okay, 1.25. So at the end, you use the solver to say, well, I'm in the critical regime, which is important to say which regime you are. And then finally, we iterate on the diameter. And then I told you we have to choose in the field the choke that has the closest size. Okay, here that was a complicated process, but we really saw that that's not really necessary. Now, yeah, the second part was liquid flow. I told you also has limited applications, but we could get from the equation an equation to give you P1 versus P2 and rate, or P2 versus P1 and rate. Available pressure and required pressure. Here we have the issue that we are not anymore on that pure high Reynolds regime, but we are on that region also. So we need to use an expression. There are many expressions. You can choose whatever you want. Here in class, we're going to use this from Poland. And we did an exercise. And this exercise was like to introduce the topic of ESP. ESP is officially covered in the advanced version. Okay, that will be advanced course. That will be next semester. But I just wanted to give you like a taste of ESP, not any calculation, but like you know how it works, so you will be a bit prepared for next. I told you that something very important about the liquid equation, that you can use it for oil-water mixture. If you stick the density, is a density that you make an average with the volume, with the volumetric fraction, sorry. So, and I told you that the same approach doesn't work very well with the density, especially because you have the wall wetting phase, and then you have this emulsion behavior that really is not linear, like I'm painting it here, but you have a maximum in between, which is very strange, but that's the way it works. You have the mixing, strong mixing, you create a very strong mix like mayonnaise, okay, and then it's very difficult to flow in the pipe. But this approach, just using this simple equation, is very useful. You sometimes can use it to model that case, okay, when you have wells that have a lot of oil and water, almost very little gas. Now, electric submersible pump, we said the configuration. We usually have the pump at the top, closest to the surface. Then we have the gas liquid separator that is needed in case there is some gas liberation here. Okay, but we try to have that the suction pressure to the pump is about the bubble point. We try, okay, because we don't like gas. Pumps don't normally like gas. But if I have any gas, I use this separator. Here comes the mixture, and then on the side comes the gas, and then the liquid continues to the pump. The pump is a multi-stage centrifugal pump. The impeller is like this size, maybe, and yeah, the fluid enters through the center and then goes on the outside due to the rotation. I told you that the pump transfers energy basically by giving kinetic energy to the fluid. You see that, and it also, but I told you it cannot give always kinetic energy, because if it does it, you increase velocity, increase, and then the friction losses, they're very high. Okay, they will be extremely high. So the way it is done is accelerated. At the same time, you have some diffusion. You convert that energy to pressure, because we said here we have high velocity, low pressure, and here we have high pressure and low velocity. Okay, so we try, it's like give kinetic energy and then recover, change, transfer to convert to pressure. Okay, then give kinetic energy, convert to pressure, and so forth. Many stages. Yes, and then we talked how it looks like. You know, here comes the fluid, goes inside the impeller, and then the impeller rotates and comes out, and then it goes to the next stage. How it looks like at the wellhead, we have our tubing and we have the cable, which is very thick, and you have to give space on the tubing hanger to fit that. Okay, so I want to talk now to refresh about performance. Okay, that I guess you had some course at some point about pump performance. Okay, but I just want to give, like, very briefly a refresher on that. ESP. So today is day 7, right? So let's write that here. Okay. Okay, and so let's say ESP performance, and it typically looks like that for the whole pump. Okay, or you will see that it works also like that for one stage. So here we have Q, which is the local rate. Okay, this is in cubic meters per day, or it can be in barrels per day. And here we have delta P. Okay, and it typically does have a shape like that. And the reason for that shape is that the pump has like it has a motor, right? It has, let's see, where is the image? Okay, we already mentioned here it has a motor someplace there. So what is the power of how can you calculate the power, the hydraulic power, if you remember that expression? The hydraulic power of a pump. The hydraulic power of a pump is the hydraulic efficiency times, sorry, not the hydraulic efficiency, but is the rate times the delta P divided by the hydraulic efficiency, right? Okay, so let's say that this is the motor. Okay, this is related to the motor power. Okay, and so it tells you that basically you can use your energy in two ways. Okay, if you have, this is fixed. Okay, you have a motor of certain size. Okay, this is usually fixed. You can use your energy in two ways. Either you can use a very high rate and a very low delta P, or you can use a very low rate and a very high delta P, or anything in between. Okay, so that's exactly what that curve is telling you. And why you say, well, why is it curved if this is a line, right? Yes? Electric submersible pump. Okay? Okay, this pump what gives energy to the fluid at the bottom hole. So why is not linear? Well, simply because the efficiency is not exactly, it's not constant. Okay, it will change with rate, and we are going to see a little bit about that. So this curve is the how how the pump performs. Okay, how it falls on a curve like that, and every point, every combination that you have in the well, okay, every Q, this is Q at the inlet of the pump, at pump inlet. Okay, so every Q star and delta P star, okay, we already saw from last class, right? If I want exactly to get this Q and that delta P, if I want to use this pump, it has to fall exactly on that line. Okay, if it doesn't fall, then it means, I cannot produce. If I want to produce that, I cannot. Okay. Okay. I won't be able to produce that because it has to fall on top of the line. However, that line is made for what we call is basically the RPMs of the pump. Okay, how fast it's rotating. But we don't use RPMs because it's going very fast. So we use frequency. Okay, which are number of cycles per second. Okay, cycles per second. Okay, so let's maybe make that here. Okay, so I have delta P, I have Q, and then I have for one frequency. Okay, if I increase the frequency, if I make it rotate faster, the curve will just scale up. Okay, and I can virtually, well, it's not like I can change it continuously, but almost continuously. Okay, so if I use another frequency, bigger, okay, it will look like that. And bigger, of course, I need more energy, and bigger will look like that. Okay, so that's F3, F2. But if I reduce the frequency at the same time, then I can get, okay, something like that. Let's call this, they're not in order, so that was not very clever on my side, but F4 and F5. Okay, so let's put here an arrow that tells me that F is increasing, F increasing. And like that, you can cover virtually almost any combination of points, right? That falls between those lines. If I want a delta P that is here, I just use a frequency between F1 and F4. Okay? If I want a point that falls here, I use a frequency F2 and F1, and so forth. Okay? Now, there are a few other things we have to take into account. Okay? Let me check. I think I had some images. No? Okay. Okay. Yeah. Now, it's not that I can go in all the range, okay, of the ESP. It's not like I can take any point. There are two very important limits, okay, that I have on my curve. So let me make it on maybe on a different plot to avoid confusion here. Okay, Q, delta P, and I have my different frequencies. Okay. Okay. First, there is a line that we call the best efficiency. That hydraulic efficiency I showed you before, there is a line, and the line usually goes through the center of the plot like that, and that's called BEL, or best efficiency line. Okay, and that's where the hydraulic efficiency is maximum. Okay, and that's usually what I want, right? Because if you see the power, okay, the hydraulic power that I require is Q delta P divided by that efficiency. So if I make that efficiency big, the power that I require will be low. That means a smaller motor. That means I don't have to put that much out of my wallet to pay for the ESP. So I try to select a point that, let's say, the delta P and Q that I want, that it will be, I try to select a pump that the efficiency line is close to that point. Okay, I have many different models, but I don't want one where the point will be too far away from the line. Otherwise, the power will be required will be very high. And there are two more lines that we have to be careful. That one of them is called like that, okay, and that's called down thrust. And there is another line on this side that is called up thrust. That usually I shouldn't operate outside of these two lines. Okay. By the way, sorry, here frequency. The frequency typically goes between any value between maybe 30 hertz. It can even go lower than that, and usually goes all the way to 70 hertz. Okay, that's the range typically of frequency. And oh yeah, I know now what I was going to show you is this plot here, should be here. Okay, the way that how you change frequency. Okay, frequency we change by changing the frequency of the electric current. Okay, so let me move that down. Okay, so you have the electricity that comes either from the national grid, it can come also from the generator, then you have a transformer, and then it goes on the voltage that is the domestic voltage or a bit higher than that, and then that goes into a unit called variable speed unit. That is very expensive part of an ESP. And here, depending, just the operator can go and change with the button. They can change the frequency and make the update every time that you need. Or it can be also connected with a remote terminal. And then it gets a signal from the operation center to change the frequency. And that feeds the electricity to the pump at the frequency that you want. So if you want to be rotating at 30, 40, 50, 60, or 70, this variable speed drive is what is reducing or increasing the frequency. Okay? So let me just make that thing here. Okay. And now we got rid of this plot. I'm not sure why. Okay, so remember, going back to this discussion, we have one line which is the best efficiency line. Okay, that's where we want to be. We want to be close to that line because this guy is going to be the smallest that it can be. Now I have two other lines, one called down thrust and one called up thrust. Okay, it should be down here. Q. Okay. And they basically, if you see, let's go back and see the impeller, okay, the way it is built. Okay, if you see the impeller, okay, that's the impeller, and it's fixed, I told you, by this key, okay, but it's fixed in the radial direction or in the tangential direction, okay, it cannot move compared to with the axis. Now, it can very well go up and down. This impeller can move up and down because it's just free. It's called like a floating impeller, okay, it can go up or it can go down. So if the rate is too high, when the fluid is entering and being deflected in the impeller, okay, let me try to make a sketch. Okay, it goes something like that. Okay, here I'm painting just half of it. Okay, and the impeller, there are two. That's the exit channel. Okay, usually no, it's not like that, but it's also like this. Let me paint it in a different color. So if the fluid that is entering through here, through this channel, if the rate is too high, it will tend to push this impeller up because remember, it is floating, okay? It's supported just by, there are some supports here. Let me just make it a bit better drawing. Okay, it has a small support here, okay? And it has also a small support here. Okay. So if the fluid is pushing it too much, then in this contact place is going to be too much friction. Okay, and it's going to, at the end, eventually cause a lot of wear on the impeller, and it's going to, at the end, you're going to damage the impeller. Okay, that is if you are below that line. Okay, if you have a rate bigger than that rate, you are going to cause that problem called upthrust, and it's called upthrust because you're pushing basically the impeller against the upper part. Okay, down thrust is the completely opposite problem. This impeller ideally should be just standing very nicely between these 2 points, okay, without very few contact. But when the rate is too low, this impeller tends to lower down and rest on this support, okay, again causing a lot of wear and eventually destroying the pump. So that's why you have these two lines, and also has to do with efficiency. Okay, so let's make that comment here. So the up thrust and down thrust limits are to avoid excessive impeller wear, okay, and damage. It will eventually fail, okay, if you operate it for too long above that rate, because there is just too much wear and it's going to them. and there is a very another important reason, and to maintain high efficiency. Okay, and that I'm going to show with another figure I have, which is very, very nice. Okay, which is this figure. Okay, and that is the flow. If you see here, that's the flow at the inlet of the pump, and that's the flow at the outlet of the impeller. Sorry, impeller, inlet, and outlet of the impeller. So when you are around this rate, okay, when you have like a medium rate, the highest efficiency, you see that the flow goes and follows exactly nicely the channel. Okay, it goes and it behaves very nice, follows exactly the channel. Now when you start to reduce the rate, it starts the flow not anymore. You see here is like is like you have, okay, if you see it from the side, the fluid is going through that channel. Okay, when you have certain rate, which is the Q nominal, okay, you are exactly aligned with that passage. So you flow and there is almost no, you go smooth with the passage. Now when the rate is smaller, okay, then you start attacking, or you start impinging into this channel on a different angle. Okay, you see here, I'm not sure if you can see, but you see that it starts to form some sort of some eddies, okay, some swirls on this side, and on this side, and here increase. So that's the main reason why the efficiency drops when you are below the nominal point, okay, below this maximum efficiency point. And at some point, these recirculations is just too much. Okay, it just causes too much drop in the efficiency. And the same thing happens if you move to the right. Okay, if you move to the right, this swirl or this channel or all of this remolino, okay, it will be formed on the other side. Okay, on the other side, because now the rate is going through the other side and is kind of impinging with a different angle. Okay, so just to summarize what we have covered so far. Okay, the curve, you have to remember, I wake you up in the middle of the night. How does it look like? Very simple. You say like IPR, okay, going down, but curve. Okay, that you have to remember. Now, what happens with the SP if we increase the frequency? Is just scaling up or scaling down. Yes, so that's how I reach different combinations of delta P and Q. Now, I cannot operate in the whole area, but there are two lines that I have to be careful, the up thrust and the down thrust. So I should be always in this range. Okay, let me mark it with, okay, I should be always in this range. Okay, and because here you have excessive wear on the due to up thrust here, and here you will have excessive wear due to down thrust. Okay. Okay, so let me make that smaller. We don't want to take the whole page. Okay, so at the end, that gives me that the area of work of the pump is something like that. Okay, that's why you see in many pump catalogs that it looks something like that. Okay, this is due to the maximum frequency. This is due to the minimum frequency. Okay, remember 30 and 60, 70, and here this is due to up thrust usually, and this is due to down thrust. Okay, and your point has to fall inside. Okay, somehow your point has to fall inside. Now, if you have, let me ask you just to see if you're awake. Okay, I'm not sure if you're awake. Okay, so I have these two pumps. I have two models, two pumps that my manufacturer is telling me that I could use. The red one, this is pump ESP1, and this is ESP2. Okay. So let's say I have a point, okay, I go to my equilibrium analysis, okay, PWF, okay, and I find the IPR. Well, it should be a straight line, right? We are talking about oil. IPR and TPR, and we know we want this Q with this delta P. Okay, and now let's say that that combination falls, let's say it falls here. Which pump should you use? Pump 1 or pump 2? 1. Why? Because you say, well, I have to check first where is the best efficiency line, right? But it will be probably much better than 2, right? Because here I'm very close to this upthrust line. That means that if I want to change the rate even a little bit, I will be already operating out of the envelope. Huh? We are? Yeah. You're awake. Yes. Okay, so that's just a small comment. You're going to cover it next semester. But be careful the curve, how it looks like, how can you regulate the rate, and then finally, the operational envelope. It's not everything, but you have something that is restricted, very limited. But you see in the manufacturer charts, you see this plot. Okay. Yeah, maybe I can show you. Let me. I think there is a nice. Okay, this is for this field that I showed you before, the Peregrino in Brazil. Let's see if they put here the curve of the pump. You see? Okay, you have 6 different pumps that each one of them have their own operational envelope. And now you know why they are. Okay, maximum frequency, minimum frequency, up thrust and down thrust, and your point has to be in between. The thing is that what is not shown here, also part of the complexity, is that when reservoir pressure goes down, right? Let's say reservoir pressure with time will go down. So you have reservoir pressure here and reservoir pressure here. So your delta P will also change, become bigger and bigger. So you will have that the points probably do something like that with time, okay? Start to go up. So you want to find a pump. So you want to find a pump that covers for most of the time of the life of your field, for most of the life of your well. If you want to produce certain rate, you want that all points will fall more or less inside that envelope. And sometimes you cannot. You have to change pump every 2 years or every 5 years. Okay, but that's the intention why people do it. And so one more thing about pump before we close, and we go to something more fun. Pump performance is affected pretty much, okay, very much by viscosity. Okay, and that's very important because pumps are normally tested with water. Thus, you will always have an effect due to the viscosity of the oil. Okay, so if we look at one particular frequency, okay, let's say F1, okay, and this is for a given viscosity 1. If you use the same frequency now, but for a higher viscosity, it will look something like that. F1, viscosity 2. And that is just because the friction, you have friction losses when the fluid goes around the passages, okay? When it goes through these passages here, it's just flowing with high velocity and it's losing energy with all the walls, okay? So when the viscosity is higher, you have more losses and less energy is transferred to the fluid, okay? So you have a decrease in the and it might very well be, if we talk about our envelope that we showed earlier, okay, that you have Q and delta P, that one looks like that, okay, for certain viscosity 1, and then for a higher viscosity, it might look something like that, okay, for viscosity 2 greater than viscosity 1. So you have to be careful, okay? You have to be correct with, you have to correct by viscosity. Okay. Any question before we leave pumps? Yeah, that will cover next semester, okay? So don't be stressed, but just to tell you that it's not so simple to find the right pump. Okay, you have to take many things into account. But at the end, you just want the point to fall inside this, okay? Inside this area. Okay, now let's move. If there are no questions, we go to multiphase, okay, which is the, let's say, it's like the most challenging and most interesting topic, because in reality we never have really we have in many cases we have single phase gas, but we never have single phase liquid. We most of the time we have multi-phase flow. Okay, so let's make a well. Okay, let's say that this is an oil well. We like to make wells, right? Just to see what's happening. Okay. And let's say that that fluid, that oil, you know about phase diagram, right? How the phase diagram looks like of a fluid. Yes, good. So it looks something like that, and then we have the dew point, okay? And this is the bubble point, and this is the dew point line. Okay? And let's say initially, here at PWF, okay, and reservoir pressure is here, and PWF, let's say, is someplace here. This is PWF, and this is PR. Now, when we flow in the wellbore, initially we might have just single phase flow, very easy to calculate. We already know how to do it, right? Now, what happens after we pass, and here we are no longer gonna be in constant temperature. In the moment we enter into the wellbore, if you remember the temperature distribution, right? If we paint the temperature distribution here, it will go from reservoir temperature down all the way to some number, right? But it will start to decrease. Therefore, you'll have an energy transfer, okay, that's of the soil, okay, of the earth. So you have an energy transfer between this, which is very hot at reservoir temperature, and this, which is less. Okay, so you have heat losses to the formation, okay, on that direction. Therefore, the temperature is also changing, and it starts to go something like that, okay? What happens when you cross this line here? When I exactly cross this line here, the bubble point line. Two phase, yes. I start to have okay, again I'm going to have mostly liquid, okay, but I'm going to have the first bubbles of gas, okay, coming out of solution. If I start coming into to the envelope, then the amount of gas will just start to come up more and more gas out of solution. And this gas, first, it will start to to it will start to make like a configuration, a flow configuration in which is just in bubbles. Okay, many bubbles, and the number of bubbles and the size of these bubbles will start to increase. Okay, what happens if I continue now a bit further down, where I have more and more gas? Okay, these bubbles of gas will start to make just bigger, even bigger bubbles, even though there are some blobs. Okay, they will start to coalesce together and form some sort of blobs. Okay. Okay. Eventually, when there are many more, I have that a flow, another pattern emerge. Okay, which is very much um, like an intermittent pattern, okay, in which I have batches of gas, okay, like these bubbles, they coalesce, they became all together. You have a big batch of gas, and then you have a big batch of liquid. Batch of gas, batch of liquid, batch of gas, batch of liquid. And at the end, it might be if the pressure, the wellhead pressure is very low, okay? That doesn't happen all the time. But here we reach wellhead pressure and wellhead temperature, okay? If it is very low, we are going to have that gas is going to be in a core in the center. All of these plugs, all of these flows, they are going to form a channel. Okay, they are going just to form a channel with some liquid droplets, and the liquid will be just sticking to the wall. Okay, so that all of that might happen in the wall. All of those things. These configurations, so these flow configurations that I have shown here, okay, I call it flow configurations, is different ways in which the flow is arranged, are called flow patterns. Okay, that's the scientific name and the name in petroleum engineering. Flow patterns. Here I have very little gas. Okay, here I have very little gas, so I just have some bubbles. That I call bubbly flow. Okay, little gas. So where should I put it? Maybe here. This is called um, bubble flow. Okay. This guy is called churn flow. Okay. This guy here is called slug flow. Okay. And this guy here is called annular flow. Okay. Depending on how much gas I have and depending how are the velocities, okay, arranged on the pipe. Now, should we try to do the gas one, right? Let's do, if we do a gas one. Okay, so we have to make our well once more. Okay, and in gas, I initially, how does the envelope look like for gas? Almost the same, right? But now the bubble point is at very low temperatures, and most of the is the dew point line, right? So if you have, let's say that reservoir pressure is here, and that's reservoir temperature. We go all the way to the bottom hole, PWF. Okay. This is PWF, still reservoir temperature. But when we start going up, so this is single phase flow of gas. Okay, what happens exactly when I enter this line, when I cross the dew point line? Here, I start to get the first droplet of liquid coming out of the gas, okay, condensing out of the gas. So I have some very fine droplets, okay, but I still have a main core of gas. Okay, what happens after? Okay, if I continue, what happens when I come inside? Do I increase the amount of liquid or not? If you remember, there are some lines here that they are ISO quality lines, right? So these lines, they are, let's say this is 100% gas, and this will be 99% gas, and this will be 98% gas. Okay? Therefore, as I enter into this envelope, I enter into that bar, I will have more and more liquid. Okay, so the next step, the liquid starts to accumulate or starts to stick to the walls. Okay, and I have this core in the center, okay, with some droplets of liquid. When the liquid is already big enough, what happens? What happened in that case? We are now very close to this case, right? But we are now, in a sense, going from here down, okay, instead of going the other way. So we can have this intermittent flow. Okay, so I have that the liquid is so much that I have all the gas is traveling in a batch, okay, and then the liquid is traveling on another batch. And if I continue, which doesn't happen very often, too much into the envelope, then I might even reach this churn flow again. Okay, but typically the one that we reach normally is, and we are going to make an exercise on that. Typically, the flow pattern we reach is a slug flow, okay, till we reach PWH and TWH. So this one, single phase gas, but this one we call it mist flow. This one we call it annular flow. Okay, and again we reach into slug flow. Okay, when there is just too much gas. Okay, so we are going to see a bit later why. So it's sometimes important, you see very clearly, right? If you have this flow pattern, you have certain pressure drop, right? But here you have another pressure drop, you have more liquid, okay? Therefore, maybe the hydrostatic pressure loss will be different than this term. So the pressure drop depends very much on what flow pattern you have and how much oil and how much gas you have in a certain position in the tubing. So that's very important, and that's the first step we're going to look into. Okay, so to calculate, basically, what do we want to calculate? The local rates, right? We want to calculate or find a way that's the starting point. We want to find the amounts. Okay, find the amounts of oil and gas at any position in the tubing. Okay, basically we want to calculate QO and QG, okay, at any pressure and temperature. That's our first goal now. Okay, we are not going to care too much about flow patterns, about delta P. We just want to know how do we calculate how much gas and how much oil, because that determines everything else. Okay, that defines everything else. We already know how to make it for only oil. We already know how to make it for only gas, but how do we deal with two guys? Okay, so that's what I want to discuss next. So a question, should we take a break? Or it's too early for a break? Too early? Okay. Break? Okay, so let's take a break, let's say 20 minutes, okay? And then we come back. Okay, so you saw now how pressure and temperature change, right, on the tubing. And now we saw the effect it has on the fluids that you have on the wellbore. And we are going to talk later about these flow configurations, okay? But they are very important to calculate the pressure drop. Okay, if you have single phase, it's very different that you have liquid with some bubbles of gas, and that's very different that if you have a core of gas and liquid going on the walls. Okay, very, very different on the pressure drop. And also the same thing happens with gas, okay? Might be outside of the envelope, but then at some point I will cross it and I will start to reduce pressure and temperature, increase the amount of gas, and I might end up eventually in this slug flow. But our first concern, let's stop that for a moment, and let's say we want to find, how do I find these amounts? Okay, how do I find oil and gas at any position in the tube, or at any pressure and temperature? We already know that we have for single phase oil, okay, we had a factor called QO at any pressure and temperature was BO times QO at standard conditions, right? And we also have that for single phase gas, we have that Q gas will be BG times QG. Okay, so we have to find something equivalent and for that we're going to introduce formally, I guess you covered some other course, the black oil model. Black oil model. Did you cover it some other place? Okay, black oil model. And it's a model we use for, we will see later the last 2 days of the course, we are going to see what we call the compositional model. There is another approach to do the same, but what we use in the oil industry is this black oil model. Okay, so let's make an experiment, okay, where we have certain amount of fluids. Okay, let's say we have, okay, let's say that we start actually with oil, right? In a container. Okay, we have oil at certain pressure, and we are going to make this experiment at pressure and at a reservoir temperature. Okay, we're going to fix temperature to avoid having too many variables. And initially, let's say that is full with just oil. So this will be P above the bubble point at reservoir pressure. Now, what happens when the pressure goes below the bubble point pressure? Okay, what we already discussed, right? Yeah, and here we can make an experiment. We can say that we have a piston, okay, and we are just lifting out that piston, right, to reduce pressure. So even, remember, the oil is not very compressible. So even if I remove the piston just a little bit, okay, if I pull it up just a little bit, that's going to cause a big decrease in pressure. Yes? So there I will start to have the first bubbles of gas. And let's say that that gas we accumulate all the way to the top. Okay, we put it at the top. And the oil, we put it here. Okay, just so we pull it up, we waited for the bubbles to go up and everything accumulated at the top and the oil is at the bottom. So that's for pressure. Let's say that's P1, P2. Okay, here P is below the bubble point pressure. So what will happen, let's paint just one more. What will happen if I continue pulling it up, okay, to reduce the pressure? The amount of gas will start to increase, right? And the amount of oil, well, will start to decrease, right? Okay, and after you have gas, actually can expand very, very much. Okay, and oil starts to take less and less until we reach, so here this will be P3, P3, TR, below the bubble point. Okay, and we repeat that experiment all the way until standard conditions. Okay, P, let's say P standard conditions and TR. And here we have a little bit of oil. Okay, and we have a lot of gas. Okay, maybe even so much that it won't fill in the cylinder. Okay, we will have a very long cylinder, to use a very long cylinder. Okay, and the final step, I just reduce the temperature in one drop. Okay, even though that's not the case, the pressure and temperature are reducing gradually. I'm just going to reduce. Yeah, I'm going to take it to standard conditions, T standard conditions. Okay, which will change a little bit, but it will still basically, it will have something like that. Okay. Now to deal with that complexity, right, that we have a phase changing and so forth, and the volumes are changing, the petroleum industry, they have defined traditionally 3 variables, okay, that we can use. One of them that we already know is called BO, and BO is defined as the volume of oil at any pressure and temperature. Okay, so in that case, it will be, let's say we're talking about P2. Okay, it will be this volume that you have here, volume of oil divided by the volume of oil at standard conditions. Okay, this volume of oil here. I create a ratio. Okay. So how will this BO look like if I paint it with versus pressure? Okay, let's say pressure and, sorry, not standard conditions, just pressure and BO. How will it look like? Okay, let's say I have PB right here. Okay, so from PB, you see that it's going to start to release oil into the gas. So you're always losing oil. Okay, so you're always reducing the volume of oil. This one will be reduced, going down, down, and this one is always the same number. Okay, this is always this guy that is here. Okay, so you're dividing something that with pressure is becoming smaller and smaller. Therefore, this gives you this behavior. Okay, something like that. Now, what happens from this point on, from this point here? You have pure oil, right? But the volume of oil is also affected by pressure. So we have that, right? We can define a variable or a thermodynamic property called the compressibility of the oil, which will be 1 over the volume of oil, okay, dVO dPO, the derivative of pressure, right? That exists for any fluid, right? For any liquid, for any gas, we have something called compressibility. And we know also that BO is just simply BO times BO, okay? One that is a constant and one that is this black oil property that I have. So CO will be, and actually here I should have a minus, okay? It's minus 1 over BO, minus 1 over BO, this is a constant, derivative of BO with respect to pressure, BO, okay, so these two, they go away, and it tells me that I can use the compressibility to calculate the variation of BO with pressure. Okay, so I integrate dBO divided by BO, that will be equal to dP times CO. Okay, and here I have, so where should I make the integral from? Or what is a good reference, okay, to start putting the snakes on that side and the snakes on that side? Where I'm going to integrate from which pressure to which pressure? A good reference point is this bubble point pressure, right? That's where it starts being pure liquid. So let's make the integral from any PV, from PV to any pressure. And here we have the BO at the bubble point, right? To any BO, to any generic BO. So that will give me, let's see if I don't make any mistakes, ln of BO minus ln of BOB, sorry, let's keep it like that, BOB equal to minus CO times P minus PB. Okay, the minus, I missed the minus someplace here. Okay, and then I apply the exponential function, give me BOB times e to the minus CO P minus PB. Okay, so you're always, this equation, if you plot it, it's something like that. It's an exponential that has the coefficient is the compressibility of the oil, and it's going all the time reduced like that. Okay, and that was just from the definition of the compressibility of a fluid. Okay, now the next step is BG, right? We define another property, so that's one property, BO, that's called oil volume factor. Okay, and remember, if P is equal to PR and T equal to TR, I call it oil formation volume factor. Okay. Now I define BG, that BG we already know what it is, right? BG will be the volume of gas divided by the volume of gas at standard conditions, right? So it will be the volume of, so what happens here when I'm below the bubble point? I have no BG, right? Because just there is no gas. Okay, so it doesn't make sense to make this Vg, but I can make it here. Okay, here is a very small volume divided by a big volume. This will be Vg. Okay. Here the volume is increasing. Therefore, how is the Vg, the behavior of Vg with pressure? We have already discussed that before. Vg versus pressure, it does something like that. Okay? Yes? And that you know also from Vg equal to P standard conditions, T standard conditions, and I had said someplace here, right? I think that's the expression, right, for Vg. Okay, until the bubble point that I have here, P bubble point, and at that point I stop having gas, no more gas. Now we come, that is no news for you, right? You already know about these two parameters. But now we go to the most important, the one that we use for, to include this change of phase. How much do we have in liquid and how much do we have in gas, in oil and in gas? And that's called RS. Okay? This one we call gas volume factor. Okay, or formation volume factor. Okay. And this RS is solution gas oil ratio. And it is defined, it's not defined between any local condition. Don't be confused, between nothing to do with local here. We're just dividing Vg at standard conditions divided by Vo at standard conditions. Okay? So we are just dividing these two guys here. And the behavior of RS, so what is the behavior of RS with pressure? Okay. RS, okay? So if let's say I take this oil, right? I take this oil and I put it at any pressure above the bubble point pressure. At any pressure higher, okay? And then I flash any of these oils to standard conditions, I'm going to get some RS, right? But I'm always going to get the same RS. The same oil, I just put it at different pressures above the bubble point. I'm always going to get these two ratio when I flash it to the surface. Okay? Now, when I flash this oil to the surface, or this oil to the surface, or this oil to the surface, what will happen then? Okay, so let's make first above the bubble point pressure. Okay, it's just constant. RS is constant, no matter what I do. Now, what happens if I take any oil below the bubble point pressure? Okay, remember I have that would be P above the PB, and then I take another oil that has already some gas. Okay, and then I just take this oil okay, this is at the pressure below the bubble point pressure. I take this oil only the oil, right? I took away the gas, and I take it all the way to standard conditions. Okay. Okay, and I'm going to get here a BO and a BG. And different that if I take this one to standard conditions. Okay, here I'm going to get another, okay, another amount of oil and another amount of gas. Okay, so that would be BO, let's call it BO star and BG star. Okay, if you see, essentially they are part of the same process, right? But here I didn't continue the whole process here. I just took away the gas and then I flushed just the oil. Okay, so which RS is going to be bigger? Is it this one, RS, or this RS star? This this guy here, it has already the maximum amount of gas it can have, right? It contains inside, it took all the gas it could take, and then it said, well, I cannot take any more gas. I'm saturated. I cannot take any more gas. This guy, I took away this amount of gas. Okay, so in theory, this RS should be, it can take some more gas yet before being saturated. Okay, so this RS is lower than this RS star. Okay, therefore the curve looks something like this. Okay, with RS with pressure. And now that's very nice, BO, BG, RS, RG, but how do we use that to calculate actually our rates? Okay, at the end we want to calculate QO and QG. Okay, so let's make it, let's say, let's make okay, using these properties we just created, okay, something crazy. The petroleum engineer defined arbitrarily these properties. So we are going to say, how do we define Q oil at the surface, okay, or the volume of oil at the surface, okay? What is that oil made up of? That oil is just made up of this oil, right? This oil is just made up of that oil that start liberating some gas, okay? But it's made up of that oil. So BO will be simply BO divided by BO, right? Yes? And nothing else. I have no oil coming from the gas. Okay? Now, sorry about that mistake. Okay. Now, the B of the gas that I have in the surface, where is that gas coming from? Okay. From any pressure and temperature, okay, let's say I'm taking here, there is actually, all the gas is coming from the oil. Okay, all of this gas that I have here is coming from this oil. Okay, so I can say, I can write the first term. RS, KBG is just RS times BO. Okay, and then BO, I can express it by the previous formula. So I can say RS times BO over BO. Okay. So we see that for And that didn't happen for oil. Okay, for the surface flow rate or for the surface volume of oil, I just had the contribution from oil. Okay, oil became smaller and smaller and smaller and eventually became surface oil. Nothing else to see. But for the gas, you see that a big contribution, part of the contribution came actually from the oil, from the local oil that was vaporizing and vaporizing and vaporizing. But not all. So if we take this point here, okay, this is correct. That equation is absolute. But if we take this point here of pressure and temperature, and we see what is this gas made of, the surface gas. It's made up of two things. The gas that will vaporize from the oil, okay, and this gas that will just simply expand. Okay? So here what we had missing in this equation is the expansion of the gas, which is Q gas divided by Vg plus Q gas divided by Vg. Sorry, volume of the gas, right? We are still talking about volumes. Okay. Now, volumes, right? And now I have a box, okay, that I'm taking to surface, bringing it up and down for my exercise. But now if I have a box through which I have flow passing, okay, it's the same thing. So the same relationship applies for Q oil. So this can be converted to Q oil, not Q gas, Q oil. Q oil divided by BO, and this Q gas will be RS divided by BO times QO plus QG divided by VG. Okay, Eureka! We found the relationship, okay, with black oil properties. We found the relationship between standard rates, that's what I measured in the surface with a test separator, with a multiphase meter, whatever method I use. But these two guys are the ones that I measured at the surface. Okay? And I can come here and I can compute these black oil properties. We're going to see soon how these are computed. Okay, I have to compute a few things, RS, BO, and BG. But then I can calculate the QO and QG, right? So how do I calculate those properties? Not yeah, I mean, how do I calculate QO and QG? Okay, I can make this in a matrix form. Okay, QO, QG is a vector, right? That depends on a matrix. That this matrix is 1 over BO 0, and here I have RS over BO and 1 over BG times QO and QG. Okay, remember matrix multiplication? The contribution of Q oil just comes this times this and this times that. No contribution for the gas whatsoever. Okay, the contribution of the gas comes this guy times this, the part that vaporized from the oil, and this guy times this, which was the part, just the expansion of the gas. Okay. And this matrix, it's as a function of pressure and temperature, a function of pressure. Now, how do we find QO and QG? What will be the expression for QO and QG? That's exactly what we want, right? We really don't have the local rates and calculate standard rates. We have the standard rates and then we calculate local rates to see what's happening in the tubing, okay, to calculate pressure drop. So what are these coefficients? Okay, I have to make matrix inversion, right? Okay, or I have to, okay, so if you take that equation simply, okay, Q oil will be BO times Q oil, okay, so BO, and here you have 0, right? Yes, simple as that. And the other equation, how do we deal with that? QG, okay, this equation, I have that QG equal to VG times QG times plus RS times QO. Okay, so here I have RS times QO, and here I have VG. Okay, I think so. You have to correct if there is any mistake, but I think it's correct. VG. Oh, sorry, VG times RS, right? Here I should have VG also. VG. RS times VG. And negative, okay, because I'm putting it on the other side. So this will be negative. Okay. So this will be negative. Okay. That clear? More or less. I create these properties, 3 properties, and then I find, I can find the local rates with these properties that I need. Yeah. Now, if you see this expansion, right, that we have assumed, so we have said we take this fluid, right, at certain pressure and temperature, and then we take it to standard conditions, okay? Okay, that's BO and PG. Okay, we took it at any pressure and temperature, or even with gas. Okay, if we had gas here, and we took it at standard conditions. Okay, if you see, we took that with constant composition. Okay, we didn't leave anything to escape. We took the oil and we expanded, and we took it to standard conditions. In reality, the way I go to standard conditions is not, this is called a CCE, or is a constant composition expansion. Okay? Because I keep the same composition in a container, I don't change it, and I expand. In reality, if you see what you have in the field, okay, I see a well, okay, here. And then I have, okay, the Christmas tree. Then I have my pipeline. So far, from here to here is all CCE. It's the same fluid, right? It's the same composition that is fluid until it reaches what? Separator. Okay, and what happens in the separator? Okay, I typically have 1, 2, 3 stages. Okay, but what I'm going to ask here we're getting some VG, right? And here we're getting some VO at the end of that complex process. The main assumption of CCE is that these two are in equilibrium. Okay? And now I ask you, are these two in equilibrium? No, right? If I mix them, they're going to reach, okay, they're going to reach that composition, right? But they will reach different amounts of oil and gas. Okay? Because here, they are in equilibrium here, and I separated them, but now they're not, after that point, they're not in equilibrium anymore. They are only in equilibrium here. Okay? Okay, and then I have another stage and another stage. Okay, they are only in equilibrium here. After that, this gas is not in equilibrium with that gas, okay, and so forth. And depending on the surface process we have, okay, that we are going to cover by the end of the week. But depending how many separator stages we have, what are the conditions of pressure and temperature? Here I have some pressure and temperature, P1, T1, P2, T2, P3, T3, okay? The ratio will change, okay? The ratio will change this ratio, okay? That's the GOR. The GOR is the VG divided by VO, okay? It's going to be different depending on what process do I have. If I have a CCE, the RS will be always the same. But if I have a complicated process in between, the RS will change depending on what kind of process do we have in the center. So to make black oil, and this is what I have in the field, okay? In the field I don't have this, I have this process. So to make it more generic, these black oil tables, I say, well, the way in which I take this mixture to the surface, I make it like that. Okay, I'm going to represent all of this by a house, okay, that I call the surface process. And then I take this oil, right? I take it through the house, and then it's going to come up with two things, with one gas, okay, and one oil, okay, which is VO, VO, and VG. Okay. And here I define, so with that I define my black oil properties, taking into account the surface process. This is the surface process. Okay. So I cannot anymore just come and flash it at pressure and temperature, but I have to go separate, 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 exactly how it is done in the field, and I find my BG, my surface conditions. Okay, so it's very important to take into account the surface process that I have in the field, and that my black oil properties are generated with that as close as possible to that process. There is one more thing that I want to make before going to the exercise, okay, which is that so far in this development we have neglected something, okay, and that something is that, where is the experiment, is here, okay. So far we have considered that that gas is always expanding, and it's always only gas, 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 gas that is growing, no problem with that gas. Sometimes what might happen is that that gas, it starts to go back to condensing, okay, start to condense liquid when I expand, okay. And that is using the phase envelope, okay. Okay, let's go to the phase envelope of a gas, okay. Sorry. Okay, if I'm reducing pressure, okay, in this case I'm keeping temperature constant, okay, I'm reducing pressure. It might be that I never have condensation of liquid, because simply the pressure is just too high. I'm outside of the envelope, okay. But in some cases, when I'm doing that, I'm actually condensing liquid, okay. Condensing liquid, and condensing liquid. So part of this liquid that I have here at surface conditions yeah, part of this liquid, part of this oil actually comes from the gas, from condensation, from retrograde condensation for the gas. And this approach is not taking that into account. Okay, so for that, people came with a second, with a modified black oil formulation. Okay, modified. Okay, in which I add a third factor called small rs. And we are seeing now how it is defined. So the way I do my experiment now, just to keep track of how much liquid comes from the gas, at any pressure and temperature, okay, I'm going to get, let's say, two phases, okay, oil and gas. So here I have a volume, local volume of oil and local volume of gas. The next step is I separate them, completely separate. At that pressure and temperature, I separate. So I will end up with one container of gas, and I will end up with one container of oil. Okay. And then I pass each one of them separately through the surface process I have, okay, through this house that has my surface process. Maybe it has only one separator stage, maybe it's two, maybe it's three, but I pass each one of them through the process separately. And I'm going to get here, okay, two things once more. I'm going to get a gas, okay, that this gas I'm going to call volume of, okay, standard condition volume of gas that comes from local gas, and I'm going to get also a liquid. Okay, and this is the oil that comes from the gas, VOG. And then from the oil, I'm going to get again two more products. That will be the gas that comes from the oil, volume of gas that comes from oil, and oil that comes from oil. So now I just made my life more complicated, okay? But I have to split because I want to know how much this gas is dropping. If this amount is very small, I don't have to use this approach, okay? But if this amount is significant, I have to use it. So this modified is for gas condensate and volatile oil, okay? When this condensation from the gas is very important. So my new black oil parameters that I define are BO will be, again, just looking at the oil, right, like we did originally. So this will be the BO divided by BO from the oil, only from the oil. Okay. The BG will be B gas divided by B only from the gas. Okay, just looking at each line separately, the top and the lower. And you have RS, which is B gas from oil divided by B oil from oil. Okay, and small rs, which is B oil from the gas divided by B gas from the gas. Okay, so I create for each one of them separately their own set of black oil properties. Yep, and of course the B oil total at surface will be B oil that comes from oil plus B oil that comes from gas, and B gas will be B gas that comes from gas plus B gas that comes from oil. Okay, so let's substitute, okay, to see now what matrix do we get. Last time we got a matrix, and we're going to do soon an exercise. So I hope this will be clear with the exercise, okay? Not. So we say BO is equal to oil from oil. What do I use to express this oil from oil? I can use BG, VO, right, times VO, just like I did before, right? This term okay. This term, I'm using it to express that because I want to have in terms of local rate. Okay, plus BOG, how can I express the oil that comes from gas? Yes, RS small times VGG, okay? But at the same time, BGG, I can express it in terms of is this expression here, right? Okay, so it can be BG times BG. Divided by BG, right? Yes? Now it's correct? Okay, so now you see I have expressed the volume of oil exactly what we have done before, right? The volume of oil at local conditions in terms of the volume of oil at standard, sorry, in terms of the local volume of oil and the local volume of gas. So we can do the same for the other volume of the gas will be gas from gas, which is Vg over Vg, right? No, no RS because this is just gas, right? Okay, plus here is the big RS times VO from oil. Yes. VO. On top, this one. Yeah, it should be divided, right? I think that is correct. Should be divided very well. VO. And here PO. Okay, and here we have RS times BOO, and that we can express as BG divided by BG plus RS, and here BOO is VO divided by VO. Yes, I think so. Okay, now I make it into rate the same way I have done before. QO QG is equal to a matrix, and the matrix is 1 over BO RS over BG, and 1 over BG, sorry, 1 over BG is here, because I'm going to multiply times QO QG, and RS over BO. Okay, and you can find the inversion of the matrix that gives you that gives you QO, QG, that gives you, so let's see, have to be careful here, BO over 1 minus RS times RS. This is Q oil. Okay, you can do it as a homework if you want, or if not, you will have to trust me. Okay, you can trust that I'm doing is fine, but you have to do quality control. So that's the thing. You have to be careful that I'm not making mistakes. Okay. So what have we done so far? Let's try to summarize to see all this crazy BO. Okay. So we did an experiment. We had already two properties, right? BO and BG. We want to use the same approach. Okay. Ratio dividing local volume by standard volume. But we have to include somehow this liberation of gas. So we made up a simple experiment, okay, that was constant composition, and we end up with, this matrix, okay, just relating the volumes, local volumes, and this RS that we introduced. We end up with this matrix, and all of us are happy. With this matrix, we can convert from local to standard conditions and from standard conditions to local. No problem. Okay. Now I told you, well, it's not really constant composition, but the composition is changing due to the surface process you have. You might have one, you might have two, depending on the process you have. So in reality, you have to calculate these local rates by taking them to a similar surface process, like the one that you have in the field, because the volumes, the standard conditions volumes of gas and oil might be very different from this experiment in a bottle. Okay, it might be very, very different. So that was one complexity. Okay, the other complexity is that the gas might be condensating some oil, okay, that we are not taking into account here. So for that, there was a modified black oil formulation introducing a small parameter called small rs, sometimes also called RV. Okay, that is very relevant for gas. You're going to be working with gas, so gas condensate and volatile oil, this is extremely important to include. Okay, but in this case, we cannot take the oil and gas together to the surface. Okay, doesn't make sense, because then we lose where the liquid is coming from. Okay, so we come and separate at pressure and temperature, and we take them to surface separately. Okay, and in that sense, we can define gas from gas, oil from gas, gas from oil, and oil from oil. And we can define our new or the same black oil properties as before, looking just at the oil separately and just at the gas separately. And we can express once more the rates, local rates, in terms of standard conditions rate and standard conditions rate instead of local rate. Okay, so I suggest now we do an exercise so that we don't stay in the theory, but we do also some exercise. Class, and this exercise is also a home exercise. You have to deliver. And we are going to work with that sheet for at least for the next today, tomorrow, and probably on Wednesday. Okay, so it's called exercise 5, and it's on my website. Multiphase P calculation. Okay, that's Exercise 5, multiphase P, calc, BO tables, reflux. Okay, so let me explain what you have here in this. We are going to use these for other things, okay? But for now, we want to use it just, we have Q oil and Q gas here, standard, measured as separator. And we have different positions in the tubing. The tubing in this case is at 3.5 kilometers. And we have both pressure and temperature. Okay? So we want to calculate, the idea is that we have here the standard conditions rate, and we want to calculate the local rate at each one of these depths, okay, at those pressures and temperatures. That's our goal. Okay, so for that we need all of these parameters: RS, small rs, BO, and BG. After we have all of that, we can apply our matrix, okay, and we can find out what is the local rate, and that we have to fill in the column number N and O. Okay, that will help me to find how much oil and how much gas you have local in that position of the tube. Now, where these properties come from? So where black oil properties come from? Okay. One option, which is the most used, is from correlation. Okay. There are many people that they made measurements for their fields. There are a few of them standing. He took his fields, well, not his fields, but from his company, and he made measurements. And he tried to develop a correlation for all of his measurements, and that was for crude oils of California. Okay, crude oils of California. Then came another guy called Glasso, Norwegian, and he made measurements for the fields in the Norwegian Sea, and then he tried to make a correlation. Okay. Then came another person in the Middle East. You have many correlations, all as many as you want. Okay, so that's one way. Okay, they try to, with field data, basically with field data, develop a correlation. Okay. Another approach is just with laboratory data. Okay. You go and you tell them to measure in a lab. There, the main difficult part is the surface process. Okay. Usually it's not reproduced. And the last option is using PVT simulator, like the ones that you're going to use later on the week. Okay. You take the composition, you have an equation of state, okay, usually here we use either Penn-Robinson or we use also SRK, Suave-Redlich-Kwong, and we artificially, using this simulator, we go through the whole process, we calculate standard volumes, and then we estimate our black oil properties. Okay, here we are going to assume you already have them from before. If you see on the second tab, BO tables, these are the tables. You can plot. We're going to see later how they look like. Okay. But yeah, so you have here these RS, small rs, BO, BG, and the densities, viscosities we need for pressure drop, and the interfacial tension we also need for later. Okay. So let's say the RS at 28 and 50. How much will that be? Big RS for 28 and 50. So we go on our column, okay, we have to find a pressure of 28, so it should be all the way to the end, 28 and 50. Okay, so the first RS is 22.55. Okay, so we can just copy, I guess we can copy all of that line. Okay, and then paste it here. Let's try like that first. Okay, the last line we copy paste because it's exactly these numbers that I have. Now let's see for 41. Okay, 41 bar. We go up and we don't have 41 actually, we have 42. And which pressure, which temperature do we need? 63. Okay, and for 63 we also don't have. We have a jump between 60 and 71. So what to do in that case? Interpolation, yes. So if you remember, we have linear interpolation, right? Interpolation that we said we have 2 points, x1 and x2, y1 and y2. Okay, and we want to find x and y. Okay, so we can use any point we want, but we say y2 minus y1, x2 minus x1 should be equal to y minus y1, x minus x1. Yeah, we clear from there. So bilinear interpolation, that's what we have to do. Okay, that we have basically x2, x1, and we have 2, right? Now we have 2 dimensions, so we have y1, y2, okay, and we have q11. Sorry, this should be x1 and x2. Okay, q or z, let's call it z. Okay, the value of, I don't want to confuse it with the deviation factor, but so you have z, which is your black hole property, x1, x2, and we have z11, z12, z21, and z22. Okay, so first, and you want it to for x and y. Okay, which is this will be pressure and this will be temperature. Okay, so first you interpolate to find this guy here, interpolate to find this guy here, you interpolate to find this guy here, interpolate to find this guy here, and finally you interpolate to find this guy in the center. Yes? Okay, so you have to apply the same equation, but you have to apply it once here between these 2 points, okay, to find this guy. You have to apply between these 2 to find this guy. Then you have to apply on this direction to find this guy, and on this direction to find this guy. And finally, you have to apply it here. Yes? But we are not going to do that, okay? We have an Excel routine to make that. Okay, so we are not going to do that because you will have to find for every point pressure and temperature, you will have to find these 4 Qs and make the interpolation. Big trouble. So let's see if that function works. Okay, so that function is called, let's click up Alt F11 and let's go down to interpolation. Okay, and I call it 2-dimension interpolation. Okay, so you have x1 will be pressure, x2, if you see how the table is you see here the table, right? X1, that's the column of pressure. X2, that's the column of temperature. And then you have several properties. Okay, you have RS, small rs, BO, and BG. Okay? You have to give the column of the property you want. Okay, so the column has to be, this is 1, 2, 3 if you want the RS, 4 if you want the small RS, 5 if you want, I think it was BO, and 6 if you want the BG. Okay, and then you have to give the whole matrix without the header, just the numbers, the whole matrix. So let's do that. Let's go back and let's do it very carefully. Okay, let's do it extremely carefully. Okay, we find our function, user defined, and we go down and we find it should be with T2, I think, 2-dimension interpolation. Okay, select it. Okay, and we start very carefully. Okay, the first one is the first column. What was it? Pressure. Okay, so we go and select the pressure that we have, this guy. Now, I want to such that when I drag that cell, not only down, but I want to drag it to the right, okay, such that it will use the other properties that I have. For that, I'm going to make a trick, okay. I'm going to say, well, pressure will always be in D, okay, always be in D. But I want the 11 to change. When I pull it down, I want it to be 12, 13, 14, etc. So I'm going to block only the D. To block only the D, I click 3 times F4. 1, 2, and 3. Until the dollar appears in front of the letter, in front of the D. That means that it's going to be blocked on the column. Doesn't matter if I drag it to the right, it will always be on D. But when I drag it down, it's going to change 11, 12, and so forth. Okay, X2, column number 2, temperature. So temperature, I take this one, and the same thing. Okay, I block the letter, not the row, not the number. So 3 times F4, 1, 2, and 3. Okay, column. Where is the property that I want? I now want to calculate RS, right? And RS was in the third column. I have it here. I put here a reminder just to be sure in which column it is. So I'm going to pick that number. And what do I want to do with that number? Block it or not? Block it, yes, but not completely. I want when I drag it down that it will not change, right? I don't want it to be pulled down. But I want when I pull it to the right that it will use the column to the right. It will change with the column. So I'm going to block it now on the number, not on the letter. So for that I use only 2 times. F4, 1, 2. Okay, now comes the very tricky part, the matrix. For the matrix, I have to go to this sheet here, and I have to go all the way to the top, select, and you can do it with the mouse. I don't have a mouse, okay, my mouse just failed on me. So I'm going to use a trick. Control Shift to the right, Control Shift down, and it selected the whole matrix. Okay, Control Shift to the right, Control Shift down, and you should have this nomenclature, BO tables A3 to 202, and then block it. The table shouldn't change, it's always the same table. Okay, just you have to drag all the matrix. Okay, you can do it. You can either select here and use the mouse. Okay, that I cannot because my Control Shift to the right, Control Shift down, and that's the whole matrix. And block it with F4. And you see now the number gives me 33.71 RS. Okay, are you getting the same number? Yeah? Okay. Now I drag it down. I cannot drag in any direction. Okay, I will have to do a trick because my mouse, I'm not sure what happens. Okay, you just drag it. You will be able to drag it. I cannot because yeah, because of issues. Okay, just drag it. You should be able to drag it. Okay. Are you getting similar numbers? Yes. Okay. Good. Okay. Scientific. Okay. Cool. Okay. We go now. Remember, here we're doing a lot of steps in one. Okay.
The second one, what should be there?
The second?
On the second one, the first column that got the results, the first one, to drag to the right.
Yeah, I drag it to the right and then I drag it down. Doesn't matter how in which order you make it. Okay, this utility is making a lot of operations at the same time. Okay, so be careful. But you know what you have to do? You have to find these four numbers on the table, and then you have to make a bilinear interpolation. Okay, but this is doing it for you, so you don't do all the repetitive work, but you do the work that is engineering. Okay, but you don't have to go on the details.
Only issue is that on the second column, we're just getting zeros on all of them. But the rest of is the same.
Yeah, you have to change the format of the number. Okay, change it here to I change it to scientific. Okay, just select the whole column, and then come here, and then check on scientific. Because this RS, remember, is the amount of oil that comes from the gas. So it's very, very small volume, a very, very small number. Okay, huh? Now it's okay. Now, why do we calculate all of these properties for? Why? What was all of our intention? Why were we doing that? Just for fun? To calculate local oil and local gas. Yes? So let's go again now, Alt F11 once more. And let's go now to, I think it's on PVT. Okay? And you see we have exactly that expression that I showed you before. Okay? Exactly that. You give RS, the small rs, sometimes called RV, BG, standard conditions gas and standard condition oil, and you calculate QG local and QO local, or the same thing. Okay, so let's use those equations for that column. Okay, it's called QG local and QO local. Okay, so let's find it. QO, user define. QO local. That depends on RS. Do I block it or not?
No.
Okay, I don't block it. I want it to be dragged down. So RS BO QG, and that QG is here, and that I have to block. Be careful. And QO is here, and that I have to block. Then okay, so I'm going to drag the oil. I just calculated the oil, and let's see what happens with the oil with pressure. It does exactly as follows the behavior of BO. Okay, when the pressure is going down, BO is also going down. Thus, the volume of the oil should also go down because it's liberating gas. Okay, so this volume should go down, and you see dramatically we lost in the. This is the bottom hole. Okay, this 3,500. There we had a 1,600 standard cubic meter per day. Okay. And when we went to the surface, we lost a third of that. The rest just evaporated, disappeared. Okay. Now let's calculate Q gas. That's Q gas local. Q gas local. It's RS RV BG, Q gas, and I block it, and Q oil, I block it. Okay, and the gas, you see the gas is doing actually the opposite. The gas follows more or less the behavior of BG, okay, where at high pressure is very low, and then when I start, it starts expanding, expanding, and also with the gas that is coming out from the oil. Okay. That clear? So now we need the first part. This exercise has many parts, and we are going to be doing, as we advance, probably tomorrow we're going to do a few, but the last one is actually this pressure that we measured. We are going to calculate in multi-phase flow. Okay, we are not just going to take those numbers, but we are going to calculate that pressure for every increment. That's the last step. But in the meantime, we have to discuss a few things to take you there. So just to summarize, we have the modified black oil formulation is this one, these two matrices. We are using actually this one. We have these rays, we measure them in surface, and we want to calculate how those rays will be in local conditions. For that we need these properties. Okay. Luckily there was something, we paid a lot of money to get this table to someone, okay, a lab, correlation, someone gave us this table, okay, but the tables, of course, they are not exactly for the pressure and temperature that I need, so I need to interpolate. For that, to make our life easy, we have this equation or this function to interpolate. We just have to know how to use it, and then with that we calculated local oil and local gas. Okay, so let's, before we abandon these properties, okay, I think we have done, what I wanted to say about them, but I just want to say how they look like. Okay, how do they look like? Okay, so we already mentioned how BO looks like. BO is here, right? RS, BG. So the only one we are really missing is the small RS. How does small RS looks like versus pressure? Hmm? Okay. Actually, it looks something like that, okay? Until you reach P, that's the dew point, okay? So RS, if it is a gas, okay? Do we give a few minutes to finish the exercise?
Okay, yes.
I suggest we make a plot just to plot these the rates, okay, with pressure, or we can plot them with depth. Actually, I think that would be better. So yeah, that's going to be tough for me. Just to see how it looks like. QO. Y1. Yeah, I'm not sure what is happening, but I don't have the mouse. So you plot it. You please do that as a homework. You have to plot. So TBD, make a plot of TBD, and here you plot QO local. Okay. And you will see basically that that number is reducing from one. I think the number is 1690 all the way to 1174, while the gas is making on the other direction. Okay, so that's oil, Q oil, and the gas will go. There is very little gas here, and then it will start and expand almost all the way here. Okay, so that will be Q gas. So this will be 138, very small number, and here you will have 4,566. Okay, you will see that the trend they go exactly the opposite. So I want to put that as a part of the homework. Okay, because just I have some issues with the mouse, and then I have to get a new mouse, or I don't know. Okay. Now you see something interesting. If you go to this Excel file, if you go to the end, all the way to the end, okay, you will see the PT diagram that we have. I have calculated for this well. Okay, you see how it looks like, and you see the bubble point. Let's take this plot to the note. Okay, let me just insert some more space. Okay, and you see exactly what I was explaining before. Okay, so what is here so what do you think is here the bottom hole pressure and the wellhead pressure? Where are we in the black line? Okay, that's the phase envelope of the fluid. This is the, as it says there, bubble point. This is the dew point. This is the critical point. Okay, what is the Greek-Condon term? You remember that the name? No? Greek-Condon term? Yes, Greek-Condon term is this value here, Greek-Condon term and Greek-Condon bar. Okay, maximum temperature, maximum pressure. Now, if this is the evolution of pressure and temperature along the wellbore, what is bottom hole pressure? It's not a trick question, okay? It should be the flow goes from high pressure to low pressure, okay? So this should be the PWF and TWF. If you don't believe, just come here and check in the data. Bottom hole pressure is 172 and 141. Okay, so it's exactly there, 140 something and 172. And we move in this direction. What happens when I move in this direction along the wellbore? Every time I get more and more gas out of solution, right? When I go deeper into the envelope, I get more and more gas. Okay, so that's exactly verifies at least our observation. Okay, before we go into something else, we go more into this multiphase. I just want to show you the behavior of RS because we discussed of small RS. Here, it is called solution oil gas ratio. Okay, this is small RS. It's called solution oil gas ratio. Okay, be careful. One is gas oil ratio, that's for the oil, and this is oil gas ratio. Oil gas, because you're interested is in this oil that comes from the gas. Okay, the behavior is something like that. Okay, if you're looking at an oil with the reservoir fluid is an oil, it usually looks something like that. Okay, and of course there is no gas above the bubble point pressure, so it's not defined. But if it's a gas, it's constant. It's just like the RS, the big RS. Okay, it's constant, and then it will start to go down, and it starts to go up again. This is due to this retrograde condensation, right? That we explained the other day in class. That in the phase envelope, okay, the lines of constant quality, they are usually like that. So when you reduce pressure, you're increasing the amount of liquid, and here you're decreasing the amount of liquid. Okay, so that's part of the behavior, like that. So before there are So two more properties are very important in black oil that we also have to generate with black oil. Okay, one of them is the viscosity of the oil, of the gas. Okay, one of them is the viscosity of the gas. Okay, and the viscosity of the gas um, what happens with the viscosity of the gas with pressure? Viscosity of the gas with pressure? Increasing or decreasing? Increasing? Okay, does something like that. And the viscosity of the oil, sure, 100%. The viscosity of the oil actually, it does the opposite. Okay? Why? Because every time you increase pressure, more gas is dissolved in solution. Okay, so it makes it lighter and it makes it kind of easier to flow. Okay, it makes it less viscous. So it goes like that, and after the bubble point, actually goes the other way, which is similar trend to the gas. Okay, just going up. And that is also, if you see on our table, that is also reported here. Okay, you see viscosity. This is a crucial property that we need for our pressure drop calculations. Okay. However, keep something in mind. So the temperature is what has the biggest effect on oil viscosity. Okay, really, the effect of pressure is not very much, but the effect of temperature is very important. So if we look at constant pressure, we see how the viscosity of the crude will look like, okay, versus temperature. And here we're talking about a log scale, which goes from, yeah, here we have maybe 1, 10, then we have 100, 1,000, then we have even 10,000, okay? You will see a behavior like that. The behavior in the first, let's say in the first range, 10 to 100, is fairly, so it's affected by temperature, but it's not so dramatic, okay? Not so dramatic. Until we reach a point that you can see in the lab, it's very, very clear to see. It's called the cloud point, okay, or also called the WAT, is the wax appearance temperature. Okay, wax appearance temperature. And at that point, so let's see, I think I have a small figure here. Okay, this is this is, you see the oil in a microscope, and you see some small particles that start to come out of solution. Initially, the oil was completely clear, and after that, it has all of these clouds of particles floating inside. And that is because, and these are very high, usually like, these are alkanes. So let me copy that photo. Okay, so that's when you start to see this. Okay, and these particles that you see here, these are Let's use another color, not black. Yeah, it was not very smart on my side. These are C12 to maybe C16 or higher. Okay, these are alkanes that they just came out of solution. Due to the low temperature, they cannot stay in the liquid phase anymore and they come out of solution. Okay? After that, everything is you will have a very abrupt increase in the viscosity. Okay? Very abrupt increase because these particles will start to make it like almost like if it was some jello, some gelatina, some that thing that you eat, right? So it's um, it's making like a jello until you reach another point, which is very important, that is called a pour point, and that's at more than 1,000 centipoise. And at that point, you reach the point where you have no more flow. Okay, no, it behaves basically like a solid. Okay, so that's the pour point. Pour comes from the word to servir. Okay, just to. Okay, so we have to be very careful. Okay, so that's the pour point. And after that, we really don't know what happens. There happens all kind of crazy things. I'm just going to put it here just for fun, the rest of the curve, but we don't care. You just have to be careful about this watt and about this pour point, okay? For two reasons. One of them is the increase in viscosity. If you have a pipeline that is getting cooled down, okay, so the reduction in temperature can cause a dramatic increase in viscosity. Thus, the pressure drop. So let's make here a small, so you have to be careful. Okay, so low temperature, that gives you high viscosity, that can give you a very high delta P in the flow line. Okay, even to stop flow completely, you cannot anymore flow that extremely high. Then there is another thing with that you have to be careful about, and that is the deposition of wax. Okay, and that is all of these particles that are floating there, they are going to tend to stick to the wall. Okay, wax are these particles that are appearing here. Okay, these particles that appear on the crude, that when you cool it down, initially is clear crude, okay, you can see through it, or yeah, you just has liquid. When you drop and the temperature drop and drop and drop, you reach this cloud point, the wax appearance temperature, that when you see that it has some particles floating on the oil. Okay, I'm not sure if that happened ever to you, but it happened in, maybe not here, but sometimes you see the oil, the cooking oil that you used to fry, sometimes has some things at the bottom. Maybe it doesn't happen here. Has to be a bit cold, okay? Maybe, yeah, less than 15 sometimes, okay? So what will happen is that all of those particles, will deposit on the wall. Okay, so this will be wax. Okay, it will tend to stick to the wall, and eventually it will stick and stick and stick until it almost plugs the pipe. Okay, so you have to be careful with wax because it will can lead to pipe blockage. Okay, pipe blockage. Okay, because the wax will stick to the wall, and it's let's see, I'm not sure if I have a figure. I think from last year we kind of covered that slightly. think we have a picture from last year. Wax, where are you, Wax? I cannot find you. Okay, that's a plug of, yeah. Okay, well, actually, that's, I heard that that's not wax, but like asphaltene, but it's something like that, okay? Stick of all of these particles, very heavy components, they stick to the wall, and then they plug the pipe. Okay, so you have to be careful in oil transportation pipeline. You have that problem, and if you know you're going to have wax, there are two solutions. Okay, if you see that you're going to have the temperature will go below the watt, then there are two solutions to isolate the pipe. Okay, you can heat the pipe. Okay, or you can perform pigging. Okay, and pigging basically is to send inside the pipe. Let's say that's your pipe, okay, and here you have some wax that formed on the walls. Okay, you send a pig which has some discs, okay, has a center part and another, okay, and you push it from behind with fluid, okay. With fluid usually is oil or water. Usually you use oil if it's a flow line. And you push it, and the pig goes scraping all of those wax from the walls. Okay, scraping, 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 all the way until the end of the flow line. Okay, so that typically, if you have, for example, on a platform, okay, if you have a platform, for example, okay, which is sending the production on a flow line to shore. Okay, here we have shore. Okay, shore, and then here we have, okay, use land. Okay, and here we have where we receive the terminal, where we receive the oil. Okay, you sometimes you send the pig every certain time. Okay, you send the pig from here all the way to the facility, such that it will push and scrap all of this wax that is stick to the wall.
But why isolate the solution?
Huh?
Why isolate the pipe?
Well, as long as it doesn't reach this point, okay, as long as the temperature doesn't reach this, you won't have wax deposition.
No, one of the solutions to put it there is isolate the pipe.
Yeah, insulate, that's very correct. Insulate the pipe, yeah. Not isolate. Insulate. Wow, that was a bad mistake. Okay, heat the pipe and pig. Okay, so this is called pigging, and you sometimes use it for subsea systems. You use it for flow lines. I think now they are thinking about installing a pipeline between Tanzania and Uganda. I think an oil pipeline, and this is one of the issues. Okay, the wax deposition on the walls. So if you know you're going to have accumulation, you have to wait until you have some layer and then you pig. If you wait too much, then remember the pig at some point, okay, let's make a, sorry for the detour, but I think pigging is important. Okay, let's say that the peak moved to another position in the pipe. Okay, let's say you have it here now. Okay, and it will have now just a block, okay, of wax in front, and it will be scrapping here now. Okay, and behind you have the oil. Okay, and if that block becomes too big, well, then you cannot push it. You're going to be stuck someplace in the pipe. Okay? If it becomes too difficult to push, then yeah, your pig is going to get stuck. That happened a few times in the North Sea, so they tried to find, but at the end they had to make a new pipeline. Okay, they just said we forget. Okay, so be careful. Hmm? No, no. Well, if you have in this case, you have a flow line, let's say that's 50 kilometers, okay? 50 kilometers. So you have one pipeline that you depend, is very expensive, $1 million every kilometer of pipe. And then you forgot to pig it after a year, and then you try to send a pig, and you just cannot push all the things that are after. So you pigging, okay? It's pigging cochino, okay? It's, in Spanish is cochino. I guess it's the same word in Portuguese. Huh? It depends on what kind of how much wax deposition you have. Okay, if you have very much, you maybe have to do it every month or every 3 months. Sometimes you can do it every 6 months.
Yeah, in this one careful. Could you please brackets because the gas
Well, this here the discussion is for oil viscosity. Okay, so this is all for oil. Okay. Yes. So yeah, that's all I had to say about properties. Um, so let's go now. Before we finish, okay, we have a few minutes left. I hope you have energy and your brain is still working. Mine is not working very well, but I'm supposed to be the teacher, so it has to work. Okay. So how now if we have our well, right? What we are doing or the purpose we are doing all of these things is equilibrium. Right? We want to design our system, we want to see, troubleshoot, etc. So let's say we have wellhead pressure constant, and here we have bottom hole pressure, and here we have PR. Okay. So let's make now with multi-phase flow. So let's say flow equilibrium. Okay, you're already complaining. I hear some people breathing hard because flow equilibrium, maybe you don't like it too much. Okay, so how does the IPR looks like? I told you for multi-phase flow, or when you have multi-phase flow in the formation, flow of oil and gas. How will it look like? Like that, okay, like gas. I told you, for liquid, the only case for liquid or high pressure gas is a straight line. For all the rest is a curve. So the IPR looks something like that. Now, how does the TPR look like? Here something very interesting happens. Okay, the available pressure, I come from this pressure and I come down until that pressure. How does it look like? Okay, well, we know if it's a single liquid or single gas, it should look like that, right? But for multi-phase flow, something extremely interesting happens. It does actually something like that. First going down and then reaches a minimum and then starts to go up. For multiphase, unique for multiphase flow. Nothing else, no gas, liquid doesn't have. It's only multiphase flow goes down and then goes up again. So I will try to explain, I will try, okay, because not always I'm successful, but I will try to explain what happens and why do you have this behavior. If you see the pipe, okay, we're going to take now a cross section of the pipe. Okay, and we always have, like I mentioned, right, oil and gas. The thing that happens is that here the oil goes very slow, okay, extremely slow, and the gas. So I'm going to put oil in you know in this color green. This is oil, and this is gas. Okay. So the oil goes very slow because it's heavy and it doesn't have too much speed, so it goes extremely slow. And the gas, it can go a bit quicker, okay, because it's lighter and it can flow a little bit quicker. The hydrostatic pressure, okay, or the delta P in multiphase flow, it has a hydrostatic component, right? Okay, and the hydrostatic is the density of the mixture times G times H, right? In this case, the density of the mixture pretty much is like oil. Okay, in this case, the density of the mixture is pretty much like oil. Okay, thus it will be very high. We are talking now about this point here. When the velocity starts to be high, two things happen. Okay, the area occupied by the oil becomes smaller. Okay, this is when Q is increased. Okay, this is not, we are talking about an oil well, so we are saying Q oil. Not sure why I wrote Q gas. Okay, when Q oil is increased, okay, two things happen. One thing, the oil starts to flow quicker. Okay, therefore, you see here it occupied like 3/4 of the pipe. By flowing quicker, okay, it occupies less of the pipe. And the gas, it will also flow quicker, but it will start to drag the oil with it. Okay, it will start to bring and pull the gas with it. Okay, by doing that, you see here that the density of the mixture now will be someplace between oil, the density of the oil, and the density of the gas. It should be the opposite, right? Density of the oil and density of the gas. Therefore, when you start increasing the velocity, the liquid starts to go faster, starts to occupy less space in the pipe, and the gas starts to go quicker, and it starts to pull the liquid up with it. Okay? Therefore, the density starts to go down, okay? And you have a reduction in the pressure, so the delta P is less, so this pressure starts to go down. Okay? It starts to be similar to PWH. Okay, starts to go down. Now, what happens from this point up here? You know, the delta P has two main components, right? Hydrostatic and friction. What do you think happens from this point here? What happens for gas or liquid, right? That the friction starts being important, okay, from this point to the right. Okay, from this point to the right, delta P of friction starts being relevant. Important. Okay, so let's make a small summary. Okay, here delta P is equal to delta P of hydrostatic plus delta P friction. Okay, and here the delta P is the same. Okay. In this regime, this one is going down, okay, because the liquid is starting to travel faster and the gas actually doesn't occupy more. It's just going faster. So this one is going down pretty much, okay, when I move on that direction, okay. This one is going down and this one is going up, but not so much, okay. This one is going up slightly. Now, when I'm in this range, this one already reached almost everything, the smallest value that it can get. But this one now is becoming very, very significant. Okay, and that's why you have the increase on the right side of the curve and the decrease of the left side of the curve. It's like you have hydrostatic. This is dominated by hydrostatic, dominated by gravity, and this is flow dominated by friction. Okay? Now, one of the complexities, so only for multi-phase flow, the curve goes down and up. Now, one of the complexities is that, for example, it can happen, the following can happen. Yes. This one and this one. Okay? This can happen. The TPR and the IPR, they can have two intersections. Okay? I have two intersections. One here and one here. Uh-oh. So which one do you think the well where I'm going to operate in this well? If I put these wells, this IPR and TPR together, where do you think they're going to operate? In Q1 or in Q2? Okay, for us it will be better if it operates in Q1, right? We get more rate, but we have to be sure how, where, when you operate on that rate. Okay, so you can derive it mathematically. Okay, but let's do like an experiment. Let's say I'm operating in this point here. Okay, let's say that somehow I push the rate a little bit to the right. I change it, okay? Change it only slightly in this point. What happens in that point? The required pressure, right, is more than the available pressure. What will happen in that case? You have less energy than what you need. What do you have to do? Reduce the rate, right? It's like you are spending here, you're in Las Vegas, spending money in the casino, etc. Then you are broke, okay? You're bankrupt. You have no more money. Then you have to start spending less, okay? Start spending less. So that one will take you back to this point. If you reduce the rate, it takes you back to that point. Now, let's say I push the rate a little bit to the left, okay? What happens here? I have more energy available than what I need. That means I have a lot of money and I can go to Las Vegas and start paying casino, etc. Right? I can increase the rate. Okay, then I go back to this point. So if you see that point, if you make a mechanical analogy, is like this situation, like a ball inside a ball. Okay, so if I move it to the right, it will still go back to the equilibrium. If I move it to the left, it will go back to the same equilibrium. So that point is what we call a stable equilibrium. Okay, because no matter how do I change, move the rate to the right or to the left, it always will tend to stay there. Now, let's do the same analysis of Las Vegas. What happens to this guy? Okay, if I move it a little bit to the right, you see, the available is now more than the required. What happens? This guy becomes crazy. I have more money than what I'm spending. I want to spend more money. Okay, and more money, and eventually I will end up here. Yes, if I start increase the rate, I will end up there. Now, what happens here in this case if I'm to the left? I have less money, the available is less than the required. That means I have to start cutting my expenses, right? Okay, but that means at the end it's going to stop producing. Yes, so if I'm in this point, it will go to the left, okay, and it will go eventually to rate 0. The well won't be producing. So this equilibrium point is like that. Okay, if I make again this mechanical analog, okay, this is an unstable equilibrium. Okay, an unstable equilibrium point.
And how do we move from one to another?
Okay, that's the tricky part. If you start flowing the well, right, let's say you stop for a long time. Okay, now you open and you say, I'm going to be rich, I'm going to produce. You're going to reach this point, right? And any change, if you move it, push it to the right somehow, with artificial lift or with something, it will reach eventually that point. But the problem might be that you're starting your well and it will go back and just simply stop. You start to start, again goes back, stops. Start to start, again you go back and stop. So sometimes you have to help these wells to start up such that they start up, let's say, in this to the right of this point, such that they reach this equilibrium. Okay, and that's very challenging. Sometimes you use all kind of methods, artificial lift. You use, but you try to bring it such that it won't, it won't be to the left of this point. Okay, I think that's all I have to say. We can take a brief summary. Today we cover a lot of things again. Okay, pumps, we talked about ESP. Not really for this course, but just I think you should be informed about ESP. Then we said we go to multiphase. It's a very complex case. We have to calculate oil, and local gas. Okay, for that we covered the traditional black oil approach. Probably you already knew from your reservoir classes. Okay, and then we calculate. For us, it's very important. This matrix is not a function of pressure only. It's also a function of temperature. Production, both pressure and temperature are changing. And you can follow this case if the oil is relatively low API, the GOR is very low, you can use it. If not, you need this new modified approach where you capture the oil that comes from the gas. We did an exercise, okay? And you had this as part of the homework to make that plot. And lastly, we talked a bit about viscosity. The temperature is very important. And not only because it can increase dramatically the pressure drop, but because you have this wax behavior. Be careful, you have this wax, and that can cause a lot of problems on the pipe. And finally, we talked about how TPR, this is TPR, okay, looks for multiphase flow, a very strange shape, okay? And we talked that that could cause that you have two equilibrium points, one stable and one unstable. Okay, see you tomorrow, and yeah, thank you for coming.